Hello students, good morning. I hope you all are safe and healthy at your home. Welcome in this lecture. We continue with our reagents. We see today number 3 polyphosphoric acid. Polyphosphoric acid. It is also known as PPA, polyphosphoric acid, and we write down structure of this reagent polyphosphoric acid OH P, sorry, it is capital P for phosphorus, P O P O P OH plus O minus OH O O minus P, this one P is plus, and this is N time P plus O minus OH. It is polyphosphoric acid PPA, polyphosphoric acid. First of all, we see preparation of polyphosphoric acid. It is also known as, otherwise we write phosphoric acid H3PO4 and it is N times. So it is known as polyphosphoric acid. First of all, we see preparation. In a preparation by stirring a mixture of anhydrous phosphoric acid H3PO4 is used as anhydrous. So anhydrous phosphoric acid and phosphorus pentoxide in proper amount. Generally it is prepared at the time of requirement. When we have requirement of polyphosphoric acid, then we get polyphosphoric acid by stirring mixture of anhydrous phosphoric acid and phosphorus pentoxide in molecular amount. So when anhydrous phosphoric acid and phosphorus pentoxide treated, we get polyphosphoric acid. Now we see the use or application of polyphosphoric acid. Polyphosphoric acid has been successfully used for various chemical reactions, the most important of which is cyclodehydration. Here note down most important application of polyphosphoric acid is cyclodehydration. Sometimes polyphosphoric acid is effective where sulfuric acid H2SO4, hydrogen fluoride HF, aluminium chloride AlCl3, etc. fail. In cyclodehydration H2SO4, in cyclodehydration H2SO4, HF and AlCl3 are failed, not used, then polyphosphoric acid is used for the cyclodehydration. Very important application of polyphosphoric acid is used in cyclodehydration. The use of polyphosphoric acid over sulfuric acid is due to the fact that it has no oxidizing power, no tendency to enter into aromatic substitution, and is less prone to promote rearrangement. It is very useful. It is used. The use of polyphosphoric acid over sulfuric acid H2SO4 is due to the fact that it has no oxidizing power, no tendency to enter into aromatic substitution, and is less prone to promote rearrangement. Moreover, it has good solvent power. Some of the important application we see here in this lecture. So, it is very important reagent for chemical conversion. We see example application of polyphosphoric acid in chemical reaction. First of all, we see cyclodehydration of carboxylic compound. Cyclodehydration of carboxylic compound. In 1932, Skoll and Mayer introduced in 1932. The name of scientist Skoll, Scholl, and Mayer introduced for the first time polyphosphoric acid as a cyclodehydrating reagent in the synthesis of dibenzochronin and chronin. Dibenzochronin and chronin. After that, the reagent has been used successfully for the synthesis of variety of compound. So, we see the synthesis of dibenzochronin and chronin. So, dibenzochronin and chronin. I write the structure, about name of scientist, and then the structure is big. So, I write down the structure. This is hexacarbocyclic. Hexacarbocyclic. Now it is treated with H2SO4. First H2SO4 at 20 degrees Celsius, and second 20% oleum. So removal of H2O molecules, we get when hexacarbocyclic compound is treated with sulfuric acid at 25 degrees Celsius and second 20% oleum, we get this type of intermediate compound. And now we treated with polyphosphoric acid. Polyphosphoric acid. About reaction. Polyphosphoric acid, PPA, or school cyclization, the name of scientist. School cyclization. School and second name is Mayer. Cyclization. With the help of polyphosphoric acid or H3PO4 P2O5, mixture of H3PO4 P2O5. First of all, this compound is converted into derivative of hexacarboxylic compounds. If we write double bond is not given by ring, then this compound is write down by this. This is dicarbocyclic compound. Dicarbocyclic compound. And this dicyclocarbic compound is treated with HI or phosphorus. In first step, it is treated with HI at 180 degrees Celsius. So, reduction of COO is converted. Reduction of COO. Here, we takes place reduction of ketonic group. And second treatment is treated with NaOH plus Cu at 500 degrees Celsius temperature. This dicarbocyclic compound is converted into dibenzcoronin. Dibenzcoronin. And we arrange double bond. Here we have some mistake. This one have only one. This is dibenzcoronin. Dibenzcoronin. So, when we treated hexacarbocyclic compound and intermediate product during the synthesis of coronin is first of all cyclized with sulfuric acid, followed by oleum, and finally with polysulfuric acid to give compound which is further converted to dibenzcoronin. Dibenzcoronin. So this is very important application which is cyclodehydration. Cyclodehydration. Now we see second example for this type of compound and about this dibenzcoronin. Second is benzoic acid to anthraquinone. Orthobenzoin benzoic acid to anthraquinone. Orthobenzoyl benzoic acid is produced by phthalic anhydride with the help of benzene. Phthalic anhydride, and this is benzene. Phthalic anhydride and benzene treated with each other in presence of anhydrous AlCl3, we get orthobenzoyl benzoic acid. Orthobenzoyl benzoic acid. Orthobenzoyl benzoic acid. Now, this orthobenzoyl benzoic acid is treated with polyphosphoric acid, H3PO4 P2O5, mixture of H3PO4 P2O5 is known as polyphosphoric acid. So this compound is converted into anthraquinone. Converted into anthraquinone. Anthraquinone. So orthobenzoyl benzoic acid is converted into anthraquinone with the help of polyphosphoric acid. Now we see next example. For cyclodehydration, phenyl butyric acid to tetralone. Phenyl butyric acid to tetralone. Phenyl butyric acid. We write down the structure of phenyl butyric acid. This is phenyl butyric acid. Is treated with polyphosphoric acid or mixture of H3PO4 P2O5. It is converted into ketone. Converted into ketone, and this is tetralone. So it is very important process for the dehydration, cyclodehydration. Now we see cyclodehydration to heterocyclic compounds. Cyclodehydration to heterocyclic compounds. We have some example for this application. So we see cyclodehydration. Polyphosphoric acid is used for synthesis of two substituted benzimidazole, benzoxazole and benzthiazole heterocyclic derivatives. Benzimidazole, benzoxazole and benzthiazole. In this unit, our second part is heterocyclic compound. So we show detail in lectures, but here we also see the application of heterocyclic compound. Cyclodehydration to heterocyclic compound with the help of polyphosphoric acid. Polyphosphoric acid. First of all, we see benzene ring contains 1 and 2 position amine group. So it is orthophenylene diamine. Orthophenylene. And it is treated with benzoic acid. Treated with benzoic acid. For here, our synthesis, we write down benzoic acid as COOH6H5. So this is benzoic acid. It is with the help of polyphosphoric acid, 250 degrees Celsius, it is converted into benzimidazole, and here our parent molecule is phenyl, so it is converted into 2-phenyl benzimidazole. 2-phenyl benzimidazole. This is 2-phenyl benzimidazole. 2-phenyl benzimidazole. So this is benzimidazole. Now second one we see for benzoxazole. Orthoaminophenol. Here compound is orthophenylene diamine, but one amino group is converted into OH, then it is orthoaminophenol. And it is treated with benzoic acid or any one compound. For this we write R. So with the help of PPA, it is converted into oxazole derivative. Oxazole derivative. And here is any one group. This is 2-alkyl benzoxazole. 2-alkyl benzoxazole. And in third application, I rearrange the board for third application. we have starting material aminothiophene, NH2SH. This is orthoaminothiophene. It is treated with benzoic acid or any compound. It is converted into alkyl benzthiazole. Alkyl benzthiazole. Two alkyl benzthiazole. So, for synthesis of two substituted heterocyclic compound, polyphosphoric acid is also a good reagent. Now we see other examples for the better knowledge. In polyphosphoric acid, we see Fischer-Indole synthesis, very important. Fischer's Indole synthesis. Fischer-Indole synthesis. Preparation of 2-phenyl indole. Preparation of 2-phenyl indole with the help of phenylhydrazone of acetophenone. Phenylhydrazone of acetophenone. This is C6H5 and CH3. Phenylhydrazone of acetophenone. Hydrazone of acetophenone is treated with polyphosphoric acid, PPA. So, phenylhydrazone of acetophenone is converted into 2-phenyl indole. 2-phenyl indole. Indole. So, this is known as Fischer-Indole synthesis, and for heterocyclic compound it is very important for this type of compound. Now we see other important examples. Polyphosphoric acid is very good solvent and catalyst for Fiddlecraft type of acylation. FIEDEL. Fiddlecraft type acylation and alkylation of phenol and their derivatives. So, with the help of anisole OCH3 is anisole. With the help of acetic anhydride and polyphosphoric acid, it is converted into Friedel-Crafts acylation and alkylation to their ethers. We saw also a second example for this Friedel-Crafts type compound, that is benzene and OH. It is known as phenol. And with the help of PPA and C6H11OH, it is cyclohexanol, PPA and 85 degrees Celsius. We get C6H11, mixture of ortho and para. Hexol compound, mixture of ortho and para component. So it is very important application. Now we see benzophenone and their derivative. Benzophenone and their derivative. Veratrol, OCH3. It is known as Veratrol. Treated with vanillinic acid. Double L, VANILLIC. With the help of polyphosphoric acid, we get benzophenone, derivative of benzophenone. This is 4-hydroxy 3 dash 4 dash trimethoxy 3 times methoxy trimethoxy benzophenone trimethoxy benzophenone. This is very important for preparation of benzophenone. So, benzophenone are prepared by interaction of phenolic ethers like veratrol and alkyl benzoic acids like vanillic acid. In presence of polyphosphoric acid, we get 4-hydroxy 3-4 trimethoxy benzophenone. So this is very important application of polyphosphoric acid. Also, we have many reactions for polyphosphoric acid, but very important useful applications for polyphosphoric acid we see esterification, nitration and hydrolysis of nitrites to amides with the help of polyphosphoric acid. So in last we see some of very important application for the polyphosphoric acid. First of all, we see conversion of salicylic acid into phenyl salicylate. Salicylic acid and phenol are treated at 90 degrees Celsius with the help of polyphosphoric acid. It is converted into ester COOC6H5 and this is phenyl salicylate. On reaction with salicylic acid and phenol, salicylic acid at 90 degrees Celsius with the help of polyphosphoric acid, we get phenyl salicylate. So this reaction is example of esterification. With the help of polyphosphoric acid, phenyl esters are obtained. We see hydrolysis of nitrile to amide. Now we see second example, nitrile to amide. This is known as hydrolysis, reaction of hydrolysis. hydrolysis of aromatic cyanide into amide. Polyphosphoric acid at 110 degrees Celsius. So CN is converted into CONH2. So this is hydrolysis of nitrile to amine. This is hydrolysis type reaction. We also see conversion of acid to amide. Acid to amide. Some of different type of aromatic acids are converted into amines. So conversion of acid into amines. Aromatic acid with the help of PPA, polyphosphoric acid, and acid with the help of HCl, NH2OH. This is acid hydroxyl amine. Acid hydroxyl amide HCl NH2OH. With the help of this compound, aromatic acid is converted into amine NH2. This is NH2 plus CO2. So this is also conversion of acid to amines, aromatic acid to amines. And with the help of nitric acid also we get derivative of nitro derivative. With the help of nitric acid and polyphosphoric acid we get nitro derivative of compounds. These are very important. Polyphosphoric acid can be used in esterification, nitration, and hydrolysis. Okay, thank you.